So we're going to finish up section 7.2 today, and then we'll look at 7.3 tomorrow and 7.4 on Thursday. Now, I just want to mention something quickly. I'm not 100% sure with the weather situation on Friday, so ideally it's not great to miss the first test of the term because I plan on missing more later on. So if something is likely going to happen with weather on Friday, then we might end up doing this test as a take-home in place of homework on Thursday night. But hopefully by Thursday I'll be able to nail that down for sure. As always, if the take-home was an issue because you don't have internet or you have to work or something like that, then you could talk to me and we could plan another time to take it. All right, but I'm assuming we're going to have more snow days, and I'd rather have more than just 2 tests or 3 tests in a term. I'd like to get 4. That's the goal. Yeah.
Do you think there's going to be a snow day Friday?
I don't know. I haven't directly watched the weather. Just a couple people have mentioned it to me. But yeah, I haven't looked at it. So I'll double check. All right, so the first thing, or kind of the big thing in this section, is taking a formula or taking an equation that has trig in it and converting it into something that doesn't have trig. So let me show you. I'm going to explain how to do it, but this is the kind of problem we're going to do. We have a formula here that has trig. And when I'm done, I want to have a formula that's just algebra. So algebra can involve adding, subtracting, multiplying, dividing, squaring, square rooting, variables. Algebra can have any of that. What an algebraic expression cannot have is trig. If it's a pure algebra expression, you can't have a sine or a cosine in it. Nothing like that. So I'm going to show you how you can get rid of trig functions in a situation like that. And when I talk about this problem, I'm going to refer to it as having an inner and an outer trig function. The inner trig function is what's on the inside, and the outer is what's in front. And the key to doing what I just said there is to start with the inner trig function. And a lot of times what we're going to want to do is take that inner trig function and use it to draw a diagram. We're going to use it to draw a diagram. Now, for the inner trig function, there's really 2 main types or 2 categories of problems you could have. The inner trig function can have inverse trig in it, or, I think that's another example with inverse, or the inner trig function can be a regular trig function. If the inner trig function has inverse trig, okay, like it does there, it's helpful to rewrite that. We can rewrite it in terms of regular trig. How do we do that? Well, we learned yesterday how to cancel out inverse trig. If you have inverse sine, you can cancel it out with regular sine. And one other thing that will come up as we solve these problems is the theorem we can use if you know 2 sides of a triangle. It'll help you get the third. And it's a theorem that applies to right triangles. Does anybody know what theorem I'm thinking of? Theorem that helps you find the third side in a triangle? Yeah, Eli?
Pythagorean?
Yeah, the Pythagorean Theorem. So the Pythagorean Theorem will be something that we use as well. It's important that we really understand the theorem because we're going to use the theorem without any numbers. Okay, we're going to use it with all letters. Okay, so keep in mind the Pythagorean Theorem as well. All right, there's not really too much more I can explain. You kind of just have to see how how this is done. So let's look at an example. We'll probably do a couple to kind of get the idea of it. But the nice thing is, once you understand how to do it, it's exactly the same every time. It never changes. So here's our problem. When I'm done, I want to have an algebraic expression in that box. That means an expression without any trig. So let's go back to the directions. Start with the inner trig function. We're going to try to make a diagram. All right, so in this case, here's my inner trig function. Whenever you use inverse trig, you are trying to figure out an angle. Okay? Forget about the sine on the outside. We'll come back to that at the end. Let's start with just this red box. If you type in inverse cosine of, pick a number, 0.7, whatever you get on your calculator when you do that is an angle. So I know that if I take the inverse cosine of something, I'm going to get an angle. So I'm basically just calling this entire red box an angle, because it will be an angle. I don't know what the angle will be, but it will be some kind of angle. Any question on that first step? You can always set an inverse trig function equal to some angle. When you don't know the angle, we usually use a Greek letter, like theta. Now, it says to rewrite the inner trig function in terms of regular trig. So what I would like to do is cancel out this cosine, inverse cosine. And what function will cancel out inverse cosine? Yeah?
Cosine?
Cosine, just the regular cosine. So the verb here is take. You're taking the cosine of each side. You are not multiplying. There's no multiplying in this whole problem. Okay? So I'm going to take and plug everything there into the cosine function. Parentheses are just used to indicate that's my argument. That's all that is. And if I take the cosine of what's on the left, I have to take the cosine of what's on the right. Regular and inverse cosine cancel each other out. So we haven't solved anything, but we have the same thing we started with, just rearranged a little bit. Now we have this. V equals cosine theta. Now, V is not a fraction. If you want to take anything and make it into a fraction, you'll see why I'm doing this in a second. But how can you take anything and make it a fraction? You can always do what? Yep.
Put it over 1.
Put it over 1. You're going to see why I did that in 60 seconds. Now, we're going to draw a diagram. I want to draw a diagram of this situation. I have an angle in a triangle, and when I take the cosine of that angle, it is supposed to come out to V over 1. What's the definition of cosine in terms of sides in a triangle? It's the what divided by the what? Yep. Yep, it's adjacent over hypotenuse. So what this equation above is saying is that when you take the cosine of the angle, the adjacent is V, and the hypotenuse is 1. So this is really telling me two sides in the triangle. The adjacent is V, and the hypotenuse is 1. Let's check it. Take the cosine of this angle. Adjacent over hypotenuse. I get V over 1 from the diagram, and V over 1 is exactly what the equation above says. So this matches. Now is where you scroll back up and you look at the original problem. They want to know the sine of theta. So look at your diagram. What's the definition of sine? Yep.
Opposite over hypotenuse.
Opposite over hypotenuse. Well, I know the hypotenuse, but I don't know the opposite. But I do know 2 out of 3 of the sides. So how can you get the third side if you know 2 of them?
Pythagorean theorem.
Yeah, we're going to do the Pythagorean Theorem. So if you want to give that left-hand side a temporary name, you can. You could call it x for now. We're going to cross that x out in a minute. But if you want to just temporarily call it x, that's fine. And Matt, can you set up my Pythagorean Theorem for me using x, v, and 1?
1 squared plus v squared
1 squared equals.
or equals v squared. And then I guess our missing variable squared, so x, I guess.
Like that?
I think that's right.
Close. We're just missing one thing. Anybody see what I'm missing there? Yep.
Addition.
Yeah, the addition sign. So 1 squared equals v squared plus x squared. Now solve that for x, and that's what you're going to put in this circle right here. And so we get 1 squared. Well, I can do 2 things at once because 1 squared is just 1. And let's bring v squared to the other side. So Tyler, how would I bring the v squared to the other side?
Subtract.
Say it again. Subtract what?
Subtract the v squared.
V squared. Yep. Let's subtract v squared from both sides. That's gone. And now I have 1 minus v squared equals x squared. Now, same kind of thing we did above earlier. I have the squaring function, and I want to get rid of it. What function cancels out squaring? Yeah,
The square root.
the square root function. So take the square root of what's on the left, take the square root of what's on the right, square and square root cancel, and you get x equals the square root of 1 minus v squared. Now I can answer whatever question they want to know because I know all my sides. Sine is opposite over hypotenuse. So I'm taking the sine of the theta in my diagram. Opposite divided by hypotenuse. Well, in this case, the hypotenuse is just 1, so I don't even need that. 1 minus v squared divided by 1. Square root. I forgot to put that in. Square root of 1 minus v squared. I put it here. I don't know why I didn't put it there. And let's check that. Let's pick a number for v that we're allowed to plug in. Remember, inverse cosine has a domain of -1 to 1. So just pick a number and try it. Let's do 0.65. Okay, 0.65. Let's take the sine of the inverse cosine of 0.65. What I'm doing is checking to see what I get with a specific number with the formula I was given, and then I'm going to check to see what I get with the formula that I figured out. And the hope is they come out the same. If they don't, then my formula is wrong. But they should be equal. All right, so let's check. 0.65, when I plug that in, I get 0.759934. All right, let's try the formula on the right. Square root of 1 minus 0.65 squared. When I hit enter, I hope I get 0.7599. Okay, let's see. And I did. So I plugged in the number on the left and on the right, and I got exactly the same answer, just to kind of double check and see if I did it right. You could check any number you want. I just picked that. And that's it. That's how you take a formula that has trig and convert it to one that doesn't. The other thing you could do is you could put this in y1 and put this in y2 and graph them. And if they graph exactly right over each other, then they're also the same thing. Okay, any questions on that one before we try another one just like that? Okay, but in general, it's the same steps every time. Set the inner trig function equal to theta, rewrite it with regular trig, draw a diagram, and then use Pythagorean theorem to get the third side. Every time. All right, let's try this one. The tangent of the inverse sine of b. Okay, can anyone tell me what my first step would be? I'll give you a hint. You can ignore tangent till the very end. You don't need that right now. Yep.
Multiply both sides by sine. Or
two things. So first, when we do a trig function on each side, remember there's no multiplication. We can take. Only time we can multiply is if we have numbers or letters. But there's something we want to do before that step. Yep.
set it equal to theta.
Yes, set the inverse sine equal theta. Now take the sine of both sides. Okay, that's the only way to cancel a function out is to take the inverse. All right, so the opposite of our function is sine. It's going to cancel out inverse. But if you do it on the left, got to make sure we do it on the right. Sarah, what does that leave me with for a new equation?
V equals sine of theta.
Perfect. V equals sine of theta. Now, I want to use that equation to do what? Yep.
Create a right triangle.
Yep. Now we're going to create a right triangle, and I want you to represent what that equation is saying in the triangle. It generally helps if you take the v and write it as a fraction. It doesn't matter where you put the theta. I mean, it can't be the 90, but you can put the theta anywhere you want. Just put it right there. They're telling me that the sine of theta equals v, and I put over 1. So what two sides am I able to label in this diagram? Yeah.
The opposite and hypotenuse.
Yes, the opposite and the hypotenuse. What is the opposite going to be?
V.
V and the hypotenuse?
1.
1. Now, if you scroll back up, this is the exact same diagram you just had. One of the legs is V, the hypotenuse is 1. One of the legs is V, the hypotenuse is 1. So if we do Pythagorean theorem, we're going to get exactly the same thing again. It's the square root of 1 minus V squared. Okay. Now we know all three sides. We have to scroll back up and see what do they really want to know. They want to know the tangent of the diagram I just drew. Okay, they want the tangent. Zach, what's my formula for tangent? Everyone, help them out. What's the tangent? Ashley?
Opposite over adjacent.
Opposite over adjacent. Yeah, not really one that I wanted to deal with. You'll see why in a second. But it is opposite divided by this. So it's V divided by the square root of 1 minus V squared. Now, as far as what I taught you, we've used everything I taught you today. But there's something else I've explained before about leaving something like this. What's wrong with that? Yep.
There's a square root in the denominator.
Right, we have a square root in the bottom, we're not supposed to leave that there, so the way we fix it, multiply the top and the bottom by the square root of what's in the bottom. Multiply top and bottom by the square root of what's in the bottom. That's going to give you v square root 1 minus v squared at the top. And what will that give me in the bottom? Yeah.
1.
Well,
1 minus v squared.
yeah, essentially it's going to give me this. You're squaring the square root of 1 minus v squared. So it gives you 1 minus v squared. And that's your final answer. So that one had one extra step compared to the last one because we couldn't leave the square root in the bottom. I'm not going to check this one, but if you typed in what's on the left in y1 and what's on the right in y2, they would look identical, the graphs. Yes?
Only the last part of in the square is the answer, right? Or is the entire thing the answer?
So the answer here is this.
Okay.
This part was originally what we had, which we thought was going to be the answer, but we ended up with a square root in the bottom we had to fix. Okay. Questions on that one? Okay. So you could make up as many of these as you want. Just pick a trig function that's a regular one on the outside, cosine. Pick an inverse trig function for the inside, inverse tangent, and we could do the cosine of inverse tangent. Right? They all work exactly the same. Does anyone want to see another one of this type, either like A or B? All right, so let's try. Let's try. I get this one. I think I'm gonna skip for now. So this is another inverse trig one, but it's a little different than the last one because it has a number. It's actually easier than when you have letters. They're both very similar. Let's do this one. The cosine of the inverse sine of 1/2. So the nice thing about this is when you draw your diagram, all the sides of the triangle are going to be numbers. No letters this time. So when we're done, the answer will be a number. No variable in your answer. All right. Can someone start me off? What's the first thing that I should do here? Okay.
Set it equal to theta.
Yeah, set what equals to theta.
The trig function.
Yep, set the inner trig function equal to theta. Okay, step one. What's my next step? Yep.
Take sine of each side.
Take the sine of each side. That's going to cancel out inverse sine on the left. And it's going to move it as a regular trig function to the right. And that's what we know when we want to do the next step. We need a regular trig function for that. So now we have 1/2 equals sine theta. Okay. What am I going to do now with that equation? I'm going to take that equation and turn it into
A right triangle.
Yep, I'm going to turn that into a right triangle. Doesn't matter where you put theta. But Francesca, what two sides have they basically given me in this equation?
The one across from the theta.
Okay, so yep, they've given me the opposite and
The adjacent?
so what's the trig function we're looking at here?
You
Just the trig function in the equation.
sine.
Yep, and what's the definition of sine? Not sure if we did that one. I know we did. Yeah, we did. Example 1a. We did sine. Not sure. You want to help her out? What's our definition for sine, Jack?
Opposite over hypotenuse.
Yep, opposite over hypotenuse. So in this case, opposite, we had that one. That's the side furthest away. And the hypotenuse is 2. Now, we need to find the cosine, but we're not ready to do that. What am I missing here that I have to figure out first? Yep,
The adjacent.
yep, I need the adjacent side. Can anyone tell me what the adjacent side would be if you use Pythagorean Theorem?
Square root of 3.
Yeah, very good. You do the square root of 3. You can always check it. If you square this, you get 3. If you square this, you get 1. 3 plus 1 gives me 4. And that's the square root of 4. Perfect. All right, so now we can figure out the cosine. Ethan, what's the definition of cosine?
Adjacent over opposite.
That's cotangent. Adjacent over opposite.
Adjacent over hypotenuse.
Yep, adjacent over hypotenuse. And Casey, what's my adjacent over my hypotenuse come out to in this case? Root 3 over 2. Yeah, very good. So the answer is root 3 over 2. Didn't need a calculator to really do any of that. Any questions on that one? All right. So last thing we're going to look at for today kind of gets us a little bit ready for what we're going to be looking at tomorrow. And that's solving trig equations. All right, so this is a review of what we did maybe in section 6 somewhere in chapter 6. Now, think about trig equations. Okay, for example, think about sine. What does the graph of sine look like? About Abigail, what does sine look like? Yeah, like a wave. Yeah, so it looks like a wave. So, let's say I had you try to solve a problem like this. Sine of x would be a wave. And what would y equals 0.5 look like? Yep.
A straight line at 0.5.
Yeah, just a horizontal line at 0.5. So if you graph this on the calculator, it would look something, just keep going. And I'd have a horizontal line at 0.5. Now, if I wanted to figure out how many solutions this problem had, and and I could zoom out forever, how many would it have? Chris? Infinite. There's infinitely many solutions. Well, focus on this section. What do we call that thing that I just put a box around? That's one what of my graph? Yep.
It's a cycle.
That's one cycle. So in order to solve a trig equation that has infinitely many answers, all you need to do is solve for the answers in one cycle. Like here and here. Now, the black answer is going to repeat again here, and it's going to repeat again here. Like this. How much later does the answer repeat? Just in general. This answer is going to repeat every what? Yeah.
Cycle.
Every cycle, whatever the cycle is. And the green answer, that's also going to repeat every cycle. So once you find the first two answers, all you have to do is tell me that they repeat every cycle. And the way we do that is once you find, let's call this answer x1, let's call this one x2. So your answers here would be, you have two answers. You'd have to do second calc intersect to get that number, whatever the x value is. You'd put whatever that number is right here, do second calc intersect, and get whatever that number is, and put that in the box. But then what you want to put on the end of it is plus the period times n. And what that means is you can add any multiple of the period to the answer you found, and you'll get an answer in a different cycle. If you add one copy of the period, that'll move you down one answer. If you add 2 copies of the period, it'll move you down 3. If you added 50 copies of the period, it would move you down to the 50th answer. So you put plus period times n. You have to fill in what the period is, though. Okay, in the sine function, it's 2 pi. Right? And you have to fill in what goes in those boxes. Okay, and I think we kind of looked at this kind of stuff earlier, so just a little bit of a review. All right, so remember, trig equations are periodic, which means they can have infinitely many solutions. We just talked about that. When you type something in on the calculator, you may have to use a reciprocal identity. What is that? Well, if I asked you to type in cotangent, you don't have a cotangent button. How do you type cotangent in on the calculator? Okay?
1 over tangent.
Yeah, that's an identity. Cotangent equals 1 over tangent. That's a reciprocal identity. Okay, so you may have to do that. So sometimes you have to put the plus 2 pi or plus the period times n. Sometimes you don't. How do you know when you should? If the problem says find every or find all solutions, you need to put plus the period times n. If the problem said find all answers between, say, 0 and pi, then that's all they want. Just the answers between 0 and 3.14. This one says all. So you have to put plus the period times n. All right. So can someone tell me what would be my first step? What do I type in first? Yeah.
Sine of x.
Okay, what is sine of x? What should I put in y2? What, Chris?
0.6.
0.6. And what should I always do next, no matter what I type in y1 and y2? I should always check this. Yeah.
Set the window to be 1 cycle.
Yeah. Set the window to exactly 1 cycle. If you look at less than 1 cycle, you may lose an answer. If you look at more than 1 cycle, you're going to be looking at extra things that just confuse you. So set your window to exactly 1 cycle. We learned when we did graphing of sine and cosine, the formula to find the length of a cycle is 2 pi over b. B is the number in front of x, which in this case is just a 1. So the length of this cycle is 2 pi. Now, that's kind of open-ended. 2 pi is the width of your window. Can somebody tell me a value I could use for the x min and a value for the x max, where the distance between them is 2 pi? Yep.
-1 and 1. Or that's for what? Never mind.
Somebody give me a window that has a width of 2 pi. Yep.
0 to 2 pi.
0 to 2 pi would be the simplest way to do it. You could go negative pi to pi. You could go 3 pi to 5 pi. It's kind of different, but usually we do 0 to 2 pi. What about the highest and the lowest? What's the range of the sine function? I want to make sure it doesn't go off the screen. Yep.
-1 and 1.
-1 and 1. I got -4 to 4. That's a little more than I need. That's okay. Point is, you're going to see exactly 1 cycle. All right. So look at that graph. And how many answers do we get per cycle in this problem? 10?
2.
2. There are 2 answers per cycle. 1 here, 1 here. Let's call those 2 answers x1 and x2. Because remember, you're solving for x. Right. How do I find x1? What do I have to do on the calculator? Well, Jack?
Find the intercept.
Yep, I'm going to find the intercept. So second calc, intersect. If you want the one on the left, you do have to move it a little closer. That should be just enough. And I get an answer of 0.64. Let's do the other one real quick. Second calc, intersect. Oops, second calc, intersect. Move it back. I think that'll be okay. 2.50. If you stop there, all you've done is tell me 2 answers to this problem. You haven't given me every single answer that there is. And there's infinitely many, so you can't write every one of them down, so we have to put something on the end of this. What's going to go on the end of each of those answers? Eli?
Period end.
Can you be more specific?
No.
Yep.
2 pi.
2 pi n, yes. You have to fill in what the period is. You can't leave the word period. So you have to put in plus 2 pi n. And what n represents here is an integer, meaning it can't be a fraction or a decimal. You can add 1 copy of 2 pi, and you'll get the answer in the next cycle. Or you could multiply this by 2 and add 2 copies of 2 pi, and you get the answer 2 cycles later. Or n could be 10, and you could get the answer 10 cycles later. But you can't add like 0.5 cycles. If you add 0.5 of a cycle, it's going to move you halfway towards the next answer. No, you have to move all the way. One full cycle. Okay? Nothing in between. And that's how you write your two answers. So the formula to find the period for sine or cosine, we use 2 pi over b. Does anybody remember what the formula is for tangent? It's very close to it, but it's just one thing is different. It's not 2 pi over b. Anyone remember that one? So it starts out t equals, and it's something we looked at in section 6.4. Yep.
Is it pi over 2?
Well, that's a specific cycle. It has a variable in it. It could be pi over 2 in a certain problem, but in general, yep.
Pi over b.
It's pi over b. So when you're dealing with tangent or cotangent, the period is found by doing pi over b. Okay. So Casey, what's b in this case? 1. So how about Matt, what's my period if my b value is 1?
This is just 1.
The b value is 1, yes. But what would my period or my cycle?
Just pi.
Yeah, just pi. Pi divided by 1, just pi. So that means when I set my window, I can do my window first. Let's get that out of the way. I want my window to have a width of pi. Abigail, how could I set my window to have a width of pi?
0 to pi.
Yeah, we could just go 0 to pi. That's the simplest way to do it. All right, and now we need to type in cotangent. I think I already asked that earlier. To type in cotangent, Jake had said it's 1 over tangent. That's how we type it in. 1 divided by tangent. And we're looking for where it hits 2.5. You got to make sure your range includes 2.5. Mine definitely does. -4 to 4. Now remember, cotangent goes up and down forever. So you're not going to be able to see the highest and the lowest. It's infinite. What you do have to be able to see is 2.5. Okay, hit graph. And you should see exactly 1 cycle. There we go. That's 1 cycle. And how many answers am I getting per cycle in this one? Okay?
1.
Just 1. Because this time there's only 1. There's your answer. You don't have to do the x1, x2 thing because there's only 1. And Francesca, how do I find that answer?
Can't you calculate the zeros on the calculator?
Well, calculating the 0 would tell me where it crosses the x-axis, which is something we do want to know sometimes. But that's not the point we want this time.
Would we do like the font then? You know how you can do like find on the calculator?
Do find.
Oh my god.
We do want to calculate.
Or like the trace button.
Well, trace can only estimate it. So like I could try, and I could say, well, it looks like it's around, 0.4 maybe, or 0.3, somewhere around 0.3, 0.4. Can someone else tell me how we get it exact? Yep, intersect. So same thing we did last time. You want to calculate the intersect.
0.
All right, so it's about 0.38. Let's go with that. Now, scroll up. all solutions. Right now, you've given me 1. What do we want to put on the end of that to represent all solutions? Yeah? Sorry?
Plus pi.
Yes, plus the period times n, and this time the period is pi. So you have to find the period first. That's important for setting your window, and it's important for what you put on the final answer. Now, this right here assumes that I'm in this. I could have done it in degrees. If I did this in degrees, I would have to set my window not to be pi units wide, but what's pi equivalent to in degrees? Yep,
180.
180. So I could do plus 180m if I was doing it in degrees. I would also have to recalculate this intercept because it wouldn't be 0.38. Right. But keep in mind, pi is usually when you're doing it in radians, and then 180 or 360, that's when you're doing it in degrees. Okay. Any questions on that? All right, so we've got just under 15 minutes left. So if you want me to take the calculators out, I can take those out, and you can practice finding intersects if you're not comfortable with it. But just let me know. I'll just unlock them, and you can borrow one and try it if you want. So those are the homework questions for tonight on 394, 37, 38, 41, 42, 45 to 47, and 49 to 52.